Uh, let's talk about correlation. And first, I think it's good to have an example that kind of motivates our talk. And so let's think about summertime as winter sets in, and let's remember the warmth and joy of eating ice cream outside and swimming. I think that's fun. So let's look at this. If we took a sample at a particular pool and said, okay, let's see how long people usually stay and how many cold beverages they drink. Okay, so let's see. Let's talk about hours of swimming. Hours of swimming. Okay, and let's let that be our x. And let's look at the number of servings of cold drink, cold beverage. We'll call that y. Okay, so this idea of correlation is based on the idea of just having a relationship between two variables. So what is like we look at all these different people and we say, okay, how many hours do they swim? How many cold drinks do they have? And so we create a set of ordered pairs, and I'm going to put it in a table form, and I'm going to say, okay, here's a quick idea, X and Y. So one person stayed 3 hours and they drank 4 cold beverages. Another person only stayed 1 hour, but they drank 2 cold beverages. Next person stayed 2 hours and didn't drink anything. It was crazy. It's like 150 degrees out there and they're not drinking. And this person stayed almost the whole day, 5 hours, and they had 8 drinks. Okay, I'll just stick with those 4. There's other people, but that's the size of our sample. So in this case, our sample is 4. And what we want to do first before correlation is we want to express the kind of, do a visual representation of the relationship. And so what we're going to do is create a scatter plot. Okay, so we have X and Y, and so let's just going to graph. This is swimming, and this is drink, beverage. Okay, so this first person, I'll do it in yellow. 3 hours and 4 drinks. 3 hours, 4 drinks. This person, 1 hour and 2 drinks. This person, 2 hours and no drinks. They're all the way down here. And this person, 5 hours and 8 drinks. That's like way up here. Okay, so looking at this, with the exception of the kind of extreme not drink person, these points fall loosely on a straight line. And I say loosely because it's not exactly a straight line, and that's the point, is that if we were to try to categorize how close to a straight line, we're really talking about correlation, and let's define that now. So when we look at these points, we want to measure a few things. One, we want to see, is this a straight line? Or how close to a straight line is this? That'll be the strength of the correlation. So we have strength. We also want to know, is it linear or not linear? So in other words, is it a straight line or not? And then we also want to know the direction. And this direction is it if we increase the value of one variable, does the other one also increase? That would be positive direction, which this one has, positive direction. Or if we increase one and the other one decreases, then it would be negative if it was moving in this direction. And I'll kind of define those in a moment. So correlation is a number that's supposed to kind of represent these 3 things. Okay, so let's talk about how it does it and give a better definition of correlation. So correlation is the measure of the strength and direction of the linear relationship between 2 variables. Okay, variables. So we're assuming that it is a linear relationship, and the way we're going to determine if something's linear or not, so just answering this question, if our correlation, which we're going to call R, this is our correlation coefficient, and we've seen this before, and r squared. That was something else, but we'll come back to that. So r, if r is close to 0, not linear. So in other words, 0 means definitely not a straight line. If it's close to 1, we're going to call this linear. And by 1, I'll define this in a moment. If the absolute value, I should say, if absolute value of r is close to 0, it's not linear. If it's close to 1, it's linear. Okay? That's how we measure the linear part. If our variable is closer to 1, then that's a stronger linear, and if it's closer to 0, then it's a weaker linear. And so the whole range in between 0 and 1 just is that kind of measurement of how close to a line is it. Okay? The other idea is whether or not the value of r is going to be positive or negative. So if it's positive, so an example would be like positive 0.30, this is telling us as x increases, y increases. So in other words, if you, in our last example, if you increase the length of time you're swimming, you probably are going to increase the number of cold drinks you consume. Negative, so an example would be negative 0.80. This would be as x increases, y decreases. Okay, so kind of a counter example, or an example for this would be increase the amount of alcohol consumed. That would be x, and then y would be decreased functionability, right? So there's a direct connection between the amount of swimming and the amount of cold beverages, or there's a direct connection between the amount of alcohol consumed and the kind of score for ability to function. Okay, both of these numbers that I have here represent something different, right? So a positive tells you it's a up and to the right kind of slant on the line, and the +3 tells you it's really spread out. The negative 0.8 is saying that it's pointing down and to the right. And the 0.8 part, the negative tells you that. The 0.8 is telling you that the points are relatively close together. They're really clustered, and they pretty much land on a straight line. Okay, you'll probably never have a correlation of 1 or -1. That's really unrealistic. Nothing is ever that perfect, but I guess you could, so I won't say you can't. Anyway, so I want to take a look at an example. This is coming out of the end of chapter exercises, and I think it's number 5. Okay, so what I want to do for number 5 is first look at creating a scatter plot in Excel. Scatter plot in Excel. Then I want to look at manually computing the correlation coefficient. So compute R in Excel by hand, and then I actually want to use the built-in Excel function. Then with Excel function, and here it is, by the way, it's equal Corel, and then you put in your x's and you put in your y's, and I'll define that in a moment. So that's what you type in. In order to compute it by hand, let's talk about the formula for correlation. Okay, so in general, the correlation is just it's basically, well, at least Pearson correlation. That's the one we're going to talk about. This is R. This is basically the variance. Well, maybe I don't want to say variance. I want to say variability. Okay, the variability of the values together. Variability of x and y together compared to the variability of them separately. The variability of x and y separately. Okay, so this thing about variance as a loose term, variance looked like this. It was the sum of squares divided by the population size. But if we do s squared, that's probably better to think about. If we do sample population, sample variance, then it's going to be divided by the degrees of freedom. Okay. Notice that when you have the ordered pairs, you have the same number of x's and the same number of y's, and so the top is going to have a particular degrees of freedom, the bottom is going to have a particular degrees of freedom, and they're going to cancel out because it's like having two fractions, a over b and c over b, which then turns into just a over c. So what we really need to do is come up with the sum of squares for the x and y together, and then figure out a way to do the sum of squares for them separately. So let's think about the sum of squares formula. Sum of squares for a variable x, and I'm going to denote it like this, looks like the values squared minus the sum squared over n. This piece here really could be separated as the sum of the x's times themselves minus the sum of the x's times the sum of the x's over n. So this would be just the essentially the variability just for x. And so SSY would look almost the same. SSY would look, replace x with a y, and there you go. Okay, and so the idea is when we want to describe the kind of variability together, we need a sum of squares for that togetherness, and so what we could do is replace one of the x's, maybe this one with a y and this one with a y, and so we create the sum of squares for the joint x and y, and we're going to call that SP for the sum of the products. Okay, sum of the squares is referencing x squared and then the sum squared, and now we have a product x times y and sum of x's times the sum of the y. So SP, sum of the products, is going to be the sum of the x's times y minus the sum of the x's times the sum of the y's divided by n. So like I said, we just replace one of the x's with a y and one of the sums with a sum of y. Okay, so the nice formula for then the Pearson correlation, R is going to be SP, so the sum of the products, SP, over the sum of the squares for the x's, the sum of the squares for the y's. But think about this a little bit. This only has one version, but this is like the sum of the x's squared, the sum of the y's squared, and so we actually have an additional squaring, and so we counteract that by square rooting the denominator. Okay, and this kind of is the idea, like why we take variance and we square root it to get standard deviation, and we're returning the appropriate units. It's the same idea as that. So let's run through an example on Excel and see how this kind of shakes out. Okay, so here it is. I've already computed. So we started with this information from the book, and the first thing they ask us to do is come up with a scatter plot. And so in Excel, you can go Insert and Scatter, and I just want the regular scatter plot, and there we go. Alright, so they don't put nice labels in there, but that's okay. I'll clean this up a bit. Let's see. No, I'll just leave it here. I'm going to change it. Location. Okay, so let's think about this. If we were trying to put a straight line kind of to represent the linear relationship, if we try to put a line like this, that doesn't do very good at representing everything. And so this idea of having a positive relationship is not good. It doesn't really work. And so what about putting a line in like this? That's a lot closer to representing the trend, right? All of these kind of are slanting down, and so the negative seems right. So this has maybe a negative association, negative direction. Okay, and then are these close together? I'm going to say not so much. So this is pretty weak. This is a weak correlation. Okay, yeah, so what we're looking for when we do the computation is that the R value is going to be pretty low. Okay, I think I need to clear this a bit. If I go back to the sheet, it stays, right? Yeah. All right, let's clean this up. All right. So I've kind of put in the formulas here to say, okay, well, if I take the sum of the x's times y, and then the sum of the x's times the sum of y's, on and so forth. So what I did is I just computed the sum of the x's, with the x and y, so it's like 1 times 7, and then 4 times 2, on and so forth. The sum of the x's, the x times x, there you go, y times y, there you go, and I just added them all up down here. Okay, so for this sum of the products, we're looking at, this is going to be 12. Whoops. It's going to be 35 minus, right? So 35 minus 28 times 168 divided by n. And if you think about this, n is 1, 2, 3, 4, 5, 6, 7, 8. 8. And we get negative 553. Okay? The sum of the x's is going to be 28 minus 12 times 12 divided by 8. That gives us 10. Sum of the y's is going to be, let's see, 30 of the y squared, so 168 minus 32 times 32 divided by 8. There we go. And so r equals, this is going to equal negative 553 divided by the square root of 10 times 4. That's not right. Let's figure that out. I see. This one should be the sum of the x times y, so that's 35 minus, and I use these, but it should be these. Okay, 12 times 32 divided by 8. There we go, substantially better. Alright, so we get a correlation coefficient of negative 0.65. That's actually better than I was expecting based on the picture. I didn't think these were that clustered, but again, never trust your eyes, always use numbers. So this is telling us that it's a negative relationship, so down and to the right. As we increase x, y responds by decreasing. And then the other thing is that having 0.65 is telling you that if you're going to maybe give it a score and how close to a straight line, it's only a 65%. So it's not horrible, but it's not that great. Okay, so it's not very clustered together. There you have it. So what I'm going to recommend is that we use built-in functions. A lot of calculators have the ability to do two variable statistics where you can type in this frequency distribution essentially, and then do some sum of squares and things like that. In Excel, we're going to use the command, let me type it in first, equals correl, and then you put in all the x's and then you put in the y's. Okay, so it's equaling correl, and then you say, okay, here are all the x's, here are all the y's, and it'll do the computation for you. There you go. Right? So it's a lot nicer to be able to just do it quickly and efficiently, and there you have it. Okay? So let me switch back over to the notes here, and what I want to do is kind of look at some other features with this R. One of the features that we want to consider is that in the past we dealt with this R squared value, okay, and we said that R squared was the percent of variation accounted for or explained, or I'm actually not quite sure how we defined it. I'm going to say that this is the percent or the fraction of variation in y explained by x. Okay, the formula for R squared in the past looked like this. It was the t squared divided by t squared plus df. Okay, and that maybe gave us a way to measure effect size. It was just kind of saying, okay, how the treatment is explaining how much of the variability, okay, or just the differences caused by the treatment is explaining how much of the variability in this model. This though is a little bit easier to say. In the past, this x was the input variable and the y was the response variable, so the experiment was inserting the presence of x to influence y. Over here, we're not claiming any sort of relationship, but it's nice that this r and this r are actually the same. And so we had in our example an r of 0.65. r squared then would be the square of 0.65, which if I had a calculator handy, that would be nice. Yeah, here we go. I should have done this ahead of time. So the square of 0.65 is 0.4225. Okay, so what that explains to us, what it tells us, is that there's only about 42% of the variance of y that can be accounted for by x changing. Okay, so what that's telling us is even though this is a having a rank of 0.65 as a straight line, the straight line is only going to explain about 42% of the variance of the y's. Okay, so this isn't very good. It's not very illuminating in terms of a relationship. Okay, we didn't have a background story on those data points, so it doesn't really help us to know, are we talking about swimming and ice cream, or are we talking about heat and swimming, or things like that. But there you have it. What's really nice then is to see this connection with the r squared, and what that's telling us is that we can actually use a t-statistic to kind of describe something about r. And so what that allows us to do is actually conduct a hypothesis test. And so this would be our last example. It's number 12 in the book. And before I jump into number 12, I just want to kind of set this up a bit. The idea here is that whenever you establish a statistic, you have some statistic, okay, we need to know, is it significant? So great, you found that the r was 0.65, but can you really trust that? And maybe you didn't have enough data points, and so the value 0.65 would be changed if we had more input. And so this statistic needs to be verified. And the only thing we can really verify is that it's not zero. Okay, so in other words, there is some connection, some linear relationship between these two variables. And so what we need to do is test if r really is zero. Okay, is this the case? And so in other words, is the correlation significant? Is correlation significant? So we're going to do a test of significance. And now we have a way to come up with a t. I'm not going to go through the algebra that converts the r squared into the t squared and whatever, but this is the way it looks. Okay, so is it significant? Here's our hypothesis. The null hypothesis would be that the population correlation is 0. By the way, this is the Greek letter rho. It's the Greek letter r. And we have this alternative hypothesis that it is not 0, greater than 0, less than 0, whatever. So this is the two-tail test, and that's what we're going to run in example 12. If you do a one-tail, you can use that. So in other words, like, we think that more drinking, the higher level of alcohol in your blood, greatly reduces your ability to function. So if we were doing this test, we would pick a one-tail test to emphasize the fact that it's a negative correlation, a negative association. Okay, so in number 12, we have some information provided. We have a sample of size 10, and the correlation coefficient was 0.6, I believe. 0.6, yeah, 0.60. Okay, and we want to test the significance. Test significance at the 5% level. Okay, or bevel if you write like I do. Alright, so our t-statistic, so our null hypothesis is that the population variance is 0 versus the alternative that it's not 0. Okay, right? And so what we're going to do is we're going to use the same model for t, except for the variance is going to be different, okay, or the standard error is going to be different. So we're going to set it up like this. We're going to have our statistic minus the hypothesized value divided by the error. Okay, and keep in mind that r squared is actually a measure of error. In fact, r is a measure of error. And so the formula for that variance or that error is going to look like this. Okay, it's going to be 1 minus r squared divided by n minus 2. There we go. Square root of all that. So for us, if our r is 0.6, let's come up with our t value. Our r is 0.6. So r is 0.6, r squared is 0.36. So this error term looks like the square root of 1 minus 0.36 out of a sample of 10, so 10 minus 2, 8. That's the square root of 0.64 out of 8, the square root of 0.08, and I think we get for our error, I don't know, let's keep it there for a second. So the t statistic, t is going to look like this. It's going to be 0.6 minus 0 divided by the square root of 0.08, which is equal to 2.12. Alright, so is that significant at the 5% level? If you think back to our t table, degrees of freedom here would be, let's see, 8. Degrees of freedom 8. So the t of 8, we throw out 1 for x and 1 for y. So t of 8 is, let's see here, now we have a t table. T of 8 and the 5% and two tails combined, it's all over here for 8, 2.306. It's saying 2.306. So the t-value of 2.306, our t-value was 2.12, so we have t equaling 2.12 is less than 2.306. That tells us that we fail to reject. In other words, we cannot determine if correlation is significant. Okay? But if we increase the sample size, so the computation would be very, very similar. If we increase the sample size, let's say, I think the book gives it at 25. So if we increase the sample to 25, we're looking now at 23. The critical t is 23, degrees of freedom 23, so we're all the way over here, 2.069. 2.069. Our t value, notice in the formula, it would change a bit, so it's going to be 0.64 divided by 24. Okay, so our t value is going to be 0.6 divided by the square root of 0.64 out of 24, which gives us, so that would be 0.6 out of 0.1633, which is 3.67. Okay, so now our t-value is greater than the critical value, which would tell us then yes, we would have enough evidence to reject the null hypothesis. So that idea is to say, okay, well, t of 3.67 exceeds the minimum 2069, and therefore we have a correlation that is significant. Okay, at the 5% level. Okay, so I want to follow up with the video on regression, so stay tuned for that. But regression is, the correlation plays a big role in regression, namely because we want to come up with that line that the correlation is measuring. So if you think back to the example of the scatter plot, you have these points with a straight line passing through them. That line, we're going to call it the best fit line. And it's the one that gives you the best description of the linear relationship between these points. And so the correlation is just measuring how good of a fit it is. And so obviously we want to take the line that has the highest correlation. And then we want to use correlation as well as the means for the x's and the y's to come up with an equation that represents this line. Okay, so we'll talk about regression. I should clarify linear regression in another video.